Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're finally going to get into some probability. Okay, the first two sections of the class dealt with arranging objects and permutations and combinations and starting to get into some of the things that are going to be useful in this class. But this is the first actual section when we actually talk about the probability of something. And the reason it's usually a little bit confusing a lot of times to people when they first study this material is that in the books, usually, you have a good chapter on probability in a few sections, and all of the different rules and all of the different little ways that you work with these things are usually presented in very short order, one after another, and they run together a lot of times is usually what happens. And so because of that, the students have a hard time figuring out what to apply to the specific problem at hand, because everything's kind of thrown at them at once and it's all new concepts. Okay, so what I've decided to do in this class is break it up methodically, step by step. And I'm hoping and I think that when we do that, we'll ease you into this topic with such confidence that by the time you get to the end of the probability, you'll be wondering why it was so hard to begin with, maybe when you first looked at it, okay? So what we're going to do here is we're going to talk about the fundamentals of probability. This section is going to be all about what is probability, okay? I think we all have some sense of what probability is. I think we all have some idea. What we're going to do in this section is nail it down to specific definitions and work some somewhat simple problems, but getting that bedrock for probability. We're going to have some other sections following on to this. We're going to get into some more details, okay? So, what is probability? Easiest thing to think about probability is probably the weatherman that you see on TV or the weather person that you see on TV, okay? They usually say, well, tomorrow is going to be partly sunny and there's a 20% chance of rain. What does that mean? What does that really mean? I mean, you know that lower numbers means less chance of something happen. And the higher numbers, like if it's 95% chance of rain, or maybe it's even 100% chance of rain, you know that it's going to rain tomorrow. I mean, there's no way. 100% means it's going to rain. There's a thunderstorm covering the entire city, no matter where you are in the city. If it's 100% chance of rain, it's going to rain, okay? And if it's 0% chance of rain, they have such confidence in the weather that's going on that they know beyond a shadow of a doubt that it is definitely not going to rain if it's 0% chance. And anything in between from 0 to 100, you know, is sort of the relative chance if it's going to happen. Now, you know that if the weather person says there's a 30% chance of rain, that it might still rain that day, okay? So what's happening when you learn about the probability is the lower numbers mean it's less likely to happen, and the higher numbers mean it's more likely to happen. But it's sort of giving you an idea on average. If you look at a whole bunch of different days in a row when they made this prediction, on average they would be right about 30% of the time. 30% of the time on average it would rain. But that doesn't mean that a storm cloud could come over your house and dump rain on your house. It could still happen. It just means that on the whole, on average, if you looked at a number of days and they made this prediction on a number of days, you know, you'd be right about 30% of the time. 30% of the time it's probably not going to rain. Doesn't mean it still couldn't happen though, okay? Another general example of probability that I know you've all done before, you flip a coin, right? There's two sides to a coin, heads or tails, right? You know from your experience that coin, when you flip it, there's roughly equal chance if it's going to land on heads or tails. You know this. So you might say to yourself, and you might have already heard, that there's a 50% chance it's going to land on heads and a 50% chance it's going to land on tails. And that's why when they start the football games off, they flip a coin, right? Because it's supposed to be random and either team has a chance to go based on that coin, okay? So that's sort of another instance of probability. So right in the middle, right there at 50%, that means that half the time it's going to land on the heads and the other half is going to land on tails. All right, so that's what a basic idea of probability is, all right? So let's nail it down into a little more kind of rigorous definition that you'll see in your books and apply it to what we have already talked about. So you've already been exposed to probability, okay? It's not this foreign thing that you won't understand. It's just we have to get the definitions, okay? So the definition of probability basically is the probability of an event. This event we're going to call A, okay? Usually in the books we call it event A. It could be event E in your book. It could be event F in your book. It doesn't matter. But usually you call it event A, most of the books. Probability of event A. It basically tells you how likely an event is to occur. It's a measure, it's a number that tells you roughly on average how likely that event A is going to occur. So we're going to be talking a lot about events in this class. What is the probability of you going to the bank and getting hit by a meteor? What is the probability that you're going to hit the lottery? And the event would be winning the lottery. Okay, so we're going to be talking a lot about events. Okay, and we've already talked about in the weatherman case that if the probability of something is 0, it's not going to happen with total certainty. Okay, if the probability of something is 100%, like in the weather center, then it is definitely for sure going to happen. It's rock solid. Anything in between is just giving you a relative indication of if that thing's going to happen. Now in probability class, you don't talk about 0% probability and 100% probability. Okay? Instead of 0 and 100%, the probabilities are all between the numbers 0 and 1. But it's exactly the same meaning, it's exactly the same scale, but instead of 0 to 100%, we always talk about probabilities between 0 and 1. Probability of 0 means 0, just like before. Probability of 1 means definitely, will, for sure, happen, no questions, for sure, will definitely happen. Okay, that's a probability of 1. All right, so the reason they use percents on TV is most people in everyday life are more accustomed to thinking in terms of percent, so that's what most people will understand. But in probability, it's between 0 and 1. Okay, so to kind of put some math behind what we're talking about here, basically, if the probability of some event A, and this is how you write it, P of A is equal to 0, okay? You read this as probability of event A. This event could be flipping a coin and getting heads. This event could be if it's going to rain tomorrow. This event could be, are you going to hit the lottery? This event could be whatever you want. Probability of event A. If it's equal to 0, then what that means is event will not, with total certainty, occur. Okay? I mean, the thing will definitely not occur. All right? Probability of something being 0, of an event being 0, would be something like Jason, who's standing right here in front of you, in the next 5 minutes is going to turn into a butterfly. Okay? That's definitely not going to happen. The probability of that event is 0. There is no chance, not even the smallest, that I'm going to turn into a butterfly. Okay? So, if the probability of some event is equal to 1, this is the maximum of the probability scale, then what it basically is saying is the event A will, with total certainty, occur. Okay? The event will occur with total certainty. Okay? All right. So anything in between 0 and 1 is going to be giving you that relative scale of if something's going to happen or not, a relative probability. Okay? Anything. So your probabilities, basically, what this is telling you is the probabilities are all going to be numbers between 0 and 1. So they're all going to be fractions, basically. Every probability is a fraction between 0 and 1, and you can also express the fractions as a decimal. So it's very common to see a probability described as, the probability of this event is 11/64. That's a valid probability. It's between 0 and 1. Or the probability of this event here, that this light bulb is going to explode, is 0.0005. Very, very low, but definitely between 0 and 1. So that's a probability of an event, okay? Now, when we're talking about probabilities, we're always going to be talking about the probability of events, and they're always going to be between 0 and 1. That's always the way it's going to be. But a lot of times, when we're especially trying to visualize what's going on, which I'm very big on myself, we use what's called a Venn diagram, okay? It's a complicated sounding name, but basically it's a picture trying to describe the event space that you're talking about here. It's actually very, very useful if you're talking about more than one event at a time. We'll get to that in the next section, but right now I want to introduce the Venn diagram to you because you'll see it pretty early on in your book. Okay, so a Venn diagram basically is a rectangle. It's not a very complicated drawing. It's a rectangle, and usually in this case, if we're talking about event A, it's going to have a circle inside. So it's a very simple little drawing. Okay, and inside the circle, usually there's a letter. So in this case, the letter will say A because this circle is representing event A, and there'll also be a number usually inside here. Let's say it's 0.4, okay? 0.4. What this is telling me is that this circle, the relative size, so to speak, of this circle, is representing the probability that this event is going to happen. The circle is bigger, it's a larger probability. If the circle is smaller, it's a smaller probability. So you can kind of think of the area of the circle being equivalent to 0.4, so that's going to have a higher probability, okay? And everything outside of this circle, let's say this has 0.6 written up there outside of the circle, but inside of this rectangle, okay? The space outside of the circle is all other events. All other events. And also you usually write that as A with a prime or A with a bar on top. You'll see it either way in your book, and it depends on what book you're using. This notation just means a complement, okay? And we're getting into some stuff. You might freak out a little bit when you read this, but this is not a big problem, big deal at all. What this is saying is, I just told you you have a probability of an event. The probabilities go from 0 to 1. So this is obviously between 0 and 1. It's actually almost 0.5, so it's a little bit less than 50% chance of happening. That's what that probability is, okay? And this circle in the Venn diagram represents the likelihood of that event happening. The larger the circle, the more likely it is. The smaller the circle, the less likely it is, okay? Everything outside the circle are all of the other possible events that can happen, okay? And, you know, for instance, if I were going to draw a Venn diagram for flipping a coin, then my event would be flipping a coin. I'd have a circle with A, and I'd have 0.5 in here because there's a 50-50 chance. 0.5 is that middle point in the probability scale. 0.5 probability of landing on heads. Let's say my event A was landing on heads. I would have a 0.5 in there. Well, I would also have a 0.5 out here because all of the other events, other than my event that I'm talking about, which is, let's say, landing on heads, all of the other possible events in that experiment is simply landing on tails. That's the only other possible event there is. And that probability of landing on tails also has 0.5 probability of happening. So what you would say is probability of event A, which could be, if I'm talking about heads and tails, would be probability of heads. Then A prime, or A with a bar on top, is going to be the complement of that event. All other events other than the one I'm talking about. So if A is heads, A prime would be tails. Okay? If probability of A is getting into a car accident on a certain day, then A prime would be the probability of not getting into a car accident. If probability of A is this light bulb exploding in the room, what's the likelihood of that happening? Then probability of A prime would be the probability of the light bulb not exploding in the room. So it's simply telling you that the circle is telling you how likely it is to happen. Everything outside is telling you everything else that can happen and the probability of that event, okay? Notice something that's very important. 0.4 in the circle and 0.6 outside the circle for this particular example that I have. There's a couple things I want to write down for you that's going to be real useful. These things are going to kind of tie into what I've drawn here, okay? And they're just sort of three little things that I've talked about most of them, but I'm going to write them down for you because you'll probably see in your book. 3 universal truths of probability, okay? Let me write it down. The probability of every single event that we're going to talk about in this class always is going to lie between 0 and 1. Okay, we've already talked about that. I'm not writing anything down that you don't already know. This is something you'll see in the book, and I'm writing it down just the way you'll see it. The probability of event A is always greater than 0 and also less than 1. That's all it's saying. And this is what I just set up here. Probability of something is 0, it's not going to occur. Probability of an event is 1, it will occur. Anything in between is the valid values of the probability. You can go from 0 to 1 inclusive. That's all that's saying, okay? All right. Now, the probability, I'm going to use some notation that some of your books will see, of the entire sample space is equal to 1. Now let me talk about what's the sample space, okay? Let's talk about heads and tails for a second, okay? When I flip a coin, how many outcomes do I have? How many different ways can the coin actually land? It can only land in 2 ways, heads or tails. That's really the only thing that can happen in that experiment, okay? So the event that I'm talking about could be the event of the success of an event could be landing on heads, and the complement would be landing on tails. The entire sample space, which is just simply all the possible outcomes that can possibly happen, only consists of 2 things, heads or tails. So the probability of S, which is just a sample space, which means the probability of everything that can happen in this experiment always has to be 1. Okay? And what that's saying is that if you look, what it's saying is a very, very simple thing there, but it's very powerful, and you must understand this, okay? Basically all it's saying is that every experiment you perform, and we're going to have lots of word problems that talk about this experiment or that experiment, what's the probability of an outcome, okay? Every one that you do is going to have so many outcomes, okay? There are going to be a finite number of outcomes, and every outcome is going to have a probability, okay? All it's saying is that that sample space of all possible outcomes in that experiment all the probabilities, if you add them all up, have to add up to 1. Okay? That's what it's saying here. Okay? That's because every probability can only go from 0 to 1, and so everything in your experiment, since there's only a finite number of ways in which the thing can happen, they must all add up to 1. That's very, very important. So 50% for heads, 50 for tails. You add them up, you get 1. 0.5 plus 0.5, you get 1. Okay? Lots of other experiments, you'll see it's the same kind of thing, but it has to work that way. Probability of the entire sample space of all possible outcomes, when you add them up, must be 1. And because of this, okay, the probability, this is a very useful thing you'll use a lot, the probability of A prime, the complement, okay, is just equal to 1 minus the probability of A happening. Okay, make sure you understand that one, okay? Think about heads or tails for a second. The probability of, let's say my event A is heads. Okay, if my probability if my event A is heads, then the complement of that is going to be all the other events is going to be tails. Okay, so if I know the probability of heads, and if the sum of all the possible outcomes in the experiment must be 1, then I can find the answer to the probability of tails by saying 1 minus the probability of heads. Okay, so it works for heads and tails as a simple example, but it really works for everything else. Maybe you have a probability of pulling, 3 jacks in a row out of a deck of cards. Let's say we could calculate that. We'll learn how to do all that stuff later, but we could calculate what is the probability of actually pulling 3 jacks in a row out of a deck. Okay, we could do that. That would be my event, pulling 3 jacks in a row out of a deck. That would be my probability of event A. Okay, once I calculate that, it's very easy to calculate the complement, which is just simply the probability of not pulling 3 jacks in a row out of the deck. And all I would do is I would take 1 and subtract the probability of the success. That would be the probability of everything else, which is the failure. Okay, so it's very, very important, and we'll work a lot of problems to get there. Okay, so we've given a general overview of what probability is. We've given a general overview of the Venn diagram. This is just sort of something to get you warm and fuzzy on it. We're going to actually use the Venn diagrams a lot more in the next section when you have 2 and 3 events going all at one time. It's pretty useful for that, okay? So what we need to talk about now is the formal definition for how to actually find and calculate the probability P of A, okay, probability of event A. And once we have that and know how to do that, we can work a lot of problems, and you'll see it's really not that big of a deal. So, okay, way we're going to do this is, okay, the following. The way you find the probability of event A, if there are n equally likely outcomes of an experiment. See, we talked about experiments. Of which one is called a success. We'll talk about this in a second. Of which one is called a success. And the success is going to be labeled with the letter S, success S, okay? Then the probability of a success is, drum roll please, probability of event A is equal to, and this is very important, in words, it's the number of ways my event A can occur divided by total number of outcomes possible. Okay? That's in words, okay? And what I'm going to go ahead and do is just write it down below. So P of A is going to be equal to, in terms of actually an equation, S, which is the number of ways my success can occur, success of my event A, divided by the total number of ways, N, that thing can happen. So let's talk about this. It's very important. You need to know this. If there are n equally likely outcomes of an experiment, of which one is called a success S, then the probability of that success is the number of ways that that event can happen, the number of ways success can happen, divided by the total number of outcomes possible, okay? The total number of outcomes possible. The event A is my success. So a lot of times in these problems, what you're going to have is you'll have a little word problem, and it'll set it up for you, and then it'll tell you, it'll say, what's the probability of this event happening? What you'll have to do is go and think about the problem and say, well, how many ways can the success actually happen, okay? And how many ways, how many total ways how many number of outcomes are there in the experiment in general, okay? And then you divide those two things, and that's what you get your probability. The simplest possible example of that would be, what is the probability of getting heads when you flip a coin one time, okay? Well, you would look at this and you would say, my event is getting a heads, okay? How many ways can that event happen, okay? Well, there's only one way it can happen. That event can only happen one possible way. When you land on the heads part of the coin, that is the only way in which that event can actually occur, okay? So you put 1 on the top, and on the bottom, the total number of outcomes possible. Well, it could land on heads, it could land on tails, so there's 2 possible outcomes to that experiment. Only one way in which success can happen, 2 ways that the experiment could end. So 1 divided by 2 gives you 1/2, and 1/2 is obviously 0.5 or 50%. So that's how you get 50% landing on heads or tails. One possible way the success can happen, and 2 ways that the experiment could actually happen, and divide those 2 things, and you get your probability. So that's what probability is, folks. I mean, the rest of the problems is just going to be practicing it. What you're going to do in every one of these problems is you're going to be looking at the number of ways the success can happen, the number of ways the experiment could actually end. You divide those 2 numbers, and that gives you a relative measure of how likely it is for that success to actually happen. So let's go ahead and work some problems and get this concept reinforced. Okay, now our first example is kind of a classic one that you'll see in every book, and you probably already talked about it even before you take this class, okay? What is the probability of drawing an ace from a deck of cards? And the deck of cards has 52 cards in it, okay? What is the probability of drawing an ace from a 52 card deck? So what we need to do is use our, what we know the probability can be defined as, and try to figure it out, okay? So the event that we're talking about, the event A, would be pulling an ace. So A is going to be defined to be pulling an ace. Okay, that's what the event A can be. Okay, so the probability of that event A is going to be equal to the number of ways the success can happen divided by the number of ways, the total number of ways that experiment could actually end. Okay, so let me ask you this. In a deck of cards, how many different ways can you pull an ace? How many different aces are there in the deck is really what you're looking at. You have a deck of cards, you have so many aces in there, and you have a whole lot of other cards in there, okay? But right now we're only concerned with how many different ways, how many different possible ways could you pull an ace out of the deck? How many aces are there in the deck is another way to say that. Well, there's 4 aces in the deck, right? There's the spades and diamonds and clubs and hearts, right? So those are the 4 ways. So you have 4 aces in the deck, okay? How many different possible outcomes of the experiment are there? In other words, how many total cards are there in the deck? That's the total number of ways that you can draw a card from the deck. That's the total number of possible ways you can do that. You have 52 cards in the deck. 52 is going to be in. Okay, so the answer is 452, 4 over 52, but you can simplify that fraction to 1 over 13. 52 divided by 4 is going to give you 13. And if you put that in your calculator, you'll see that it's 0.07. Now, usually, so the answer is 1/13 or 0.07. Usually we leave the probabilities in terms of a fraction when you can. I'm just sort of converting it to a decimal to show you. It's a pretty small number, less than 1/10, okay? So the chance of pulling a single ace out of a deck of cards is going to be less than 1 in 10. Okay, it's 1 in 13 times you'll actually do that if you shuffle the deck properly and everything is completely random. So all we did, we applied what we knew. This is the number of ways the success can happen. This is the total number of ways the experiment could happen as a result. There's 4 aces in the deck. There's 52 total possible cards. The comparison of these two things with this fraction is what the probability is defined as. Okay, so if we know what the probability of the event is, let me ask you this. What would be, as a follow-up question, what would be the probability of, on a single draw, not pulling an ace from a deck of cards? Not pulling an ace from a deck of cards. Well, the easiest way to do that is, if the probability of event A is pulling an ace, then A prime is not pulling an ace. I mean, that's just the way it is. If A is defined as pulling an ace, A prime, which is the complement, is not pulling an ace. It's every other possible outcome other than the one we have. And from our previous board, the probability of A prime is 1 minus the probability of A happening itself, because the sum of both probabilities together must be equal to 1, because the sum of all the outcomes in the experiment has to always equal 1. So this is going to be 1 minus the probability of event A we just found, 1 over 13. Okay? So we can do this subtraction simply by writing the 1 as 13 over 13 minus 1 over 13. 13 minus 1, I did that because I wanted a common denominator. 13 minus 1 is 12 over 13. So the probability of A prime is equal to 12 over 13. So the probability of not drawing an ace is 12 over 13. Notice that this is actually very close to 1. 13 over 13 would be 1. This is 12 over 13, so it's very close to 1. And that makes sense, because if you have a deck of cards, there's a whole lot more likely that you're not going to draw an ace, right? Because there's so many other cards in the deck other than aces. Very likely that you'll actually pull an 8 or a 7 or a jack or something else other than an ace. So the probability shows you that. It's very close to 1. Which means you're very likely not going to pull an ace, okay? Now, one more thing I'm going to show you here. You can do it this way. You can do the subtraction and get the answer, but what if we did not want to do that? What if the problem just outright was, what's the probability of not pulling an ace from a deck? Well, we could do the S over N just as before. Let me ask you this. We know there's 52 cards in the deck, so N is going to be 52, but if I want to know what the probability of not pulling an ace, I would need to know the number of ways you cannot pull an ace. Well, there's 52 cards in the deck minus 4 aces. This is the total number of cards other than an ace, basically, in the deck. So you have 48 over 52. In other words, there's 48 cards in the deck that are not an ace, and there's 52 total cards. So you divide those two things together, all right? And when you simplify this fraction, you're going to get the same 12 over 13. Okay, so there's more than one way to solve a problem in every case. I mean, I just wanted to start at the beginning and show you the probability of getting an ace was 1/13. If you wanted to find the probability of not getting an ace, you do 1 minus the probability of the event is going to be equal to its complement, which is not pulling the ace. You can get the answer. Or if you just wanted to start from scratch, you could just say, well, this is the number of ways the success can happen. This is the total number of ways the experiment can happen. There's 48 cards in the deck that are not an ace. And so there's 52 total cards, so you do that and you get the same exact answer. So again, in every one of these problems, we're going to do the same thing. We're going to identify the number of ways the success can happen and the total number of outcomes, and that's what we're going to do. The next problem says, what is the probability that you guess the day of your friend's birthday, not including the year? So your friend comes up to you and says, I'm your new best friend. What's my birthday? Well, you know that the odds of guessing their birthday is extremely low, right? But how do you actually calculate the probability? Well, what you would do is you would say the probability of that event A, where the event A is the event is guessing your friend's birthday correct, is going to be equal to the number of ways that you can successfully do that divided by the total number of ways in which that little experiment can end, the total number of guesses, basically. How many answers are there to that problem? What is your birthday? Well, there's only one answer to that problem. So 1 divided by how many different ways could I answer? Well, there's 365 days in a year. So 1 out of 365. And that's the answer. That is the probability of me guessing my friend's birthday purely randomly. And if I wanted to convert that to decimal, it would be 0.0027. And you can see it's a very small number, very close to 0. So the odds are very, very low that you'll guess someone's birthday just by guessing. Okay? And as a follow-up, what is the probability that when you do this, you're actually wrong? So he or she says, well, what's my birthday? And you say, June 17th. What is the probability that you're wrong? Okay, well, it's very likely you're going to be wrong. I mean, you know that. What is the actual way to calculate that? Well, if A is the probability of guessing her birthday, then the probability of A prime is going to be the probability of not guessing her birthday. Okay. A complement is all other outcomes other than your event. So this is guessing my birthday, this is not guessing my birthday. Okay? I can calculate it as 1 minus the probability of guessing the birthday. Okay? So it's going to be 1 minus 1 over 365. And in order to do this, I'm just going to find a common denominator by taking 365 divided by 365, that's equal to 1. I'm just rewriting that. Minus 1 over 365. So on the top, 365 minus 1 is 364 over 365, which is the answer. And if you convert that to an actual decimal, you get 0.997. So very, very, very close to 1, but not quite 1. So what this means is the probability of incorrectly guessing her birthday, in other words, being wrong, is very, very high. It's very close to 1. And that just means that it's very likely you'll be wrong when you do that, okay? So probability of guessing her birthday right is low. 1 minus that probability gives you the probability of being wrong. You do this math and you get the answer. And also notice that if you had just wanted to, if this were the original problem, and I just asked you what's the probability of being wrong, S over N. There's 365 answers. And if you're incorrectly guessing her birthday, there's 364 ways to do that because those are all the wrong answers. So this is S over N, just like you would expect. There's nothing magical or fancy about it. I'm just showing you 2 different ways to do the same problem, okay? So the next problem says, if you randomly pick a person off the street, what is the probability that their birthday occurs in June? Okay? So it's the same kind of problem. Somebody comes up to you and you're just going to guess and say, well, your birthday's in January. What is the probability that their birthday is actually in June, just on average? And also I want you to assume for this problem that all of the months have the same exact number of days in them, just to make them all equally likely to occur. Because you know February has less days than December, for instance. We want to make sure we're going to just pretend all the months have exactly the same number of days. So in this problem, if my event A is that this person, this random person that walks up to me has a birthday in June, A would be the probability that that's the case, okay? So it's going to be the number of ways that can happen divided by the total number of outcomes, okay? And how many different ways can that happen? Well, there's 12 months in the year, okay? And if her birthday's in June, there's only one answer. That would be that her birthday's in June. How many different possible ways could this experiment end? Well, there's 12 months in the year. There's 12 different answers for what month her birthday's in. So the probability of being in June is 1/12 because there's only one way that you can get a birthday in June out of 12 possible months, okay? All right, and if you just wanted to also calculate the probability that this random person's birthday is not in June, then what you would be looking for is the probability of A prime, okay, which is the probability that it's not in June. And you can do that by 1 minus P of A, 1 minus the probability of it being in June, which is 1 minus 1/12. And to do that subtraction, you just rewrite 1 as 12 over 12 minus 1 over 12. 12 minus 1 is 11 over 12. This is the probability that it's not in June. So if a person randomly comes up to you on the street, the probability of their birthday not being in June is very high. It's almost 1. And that means it's very likely to be the case because it just makes sense. I mean, you know, there's 12 months in a year. What are the odds that somebody has a birthday in June? Not too high. Okay, it's very likely that if you're trying to guess if their birthday's in June or if their birthday's in June or not, it's very likely going to be low. 1/12 is a pretty low number, and that's what that's trying to convey. The next problem says you roll a 6-sided die, just a regular die that you would get from a board game. You roll it, and it has 6 sides. Okay, what is the probability that you're going to roll a 3? Okay, what is the probability that you're going to roll a 3? So it's the same kind of thing. As always, the probability of my event A, when my event here is the probability of rolling a 3. That's what my event is. And I'm going to calculate that by looking at the number of ways that event can happen divided by the total number of outcomes in that experiment of rolling a die. Okay? How many ways can I get a 1? I'm sorry, how many ways can I get the number 3? Well, there's 6 numbers on the die. There's only one way to roll the number 3. Okay? And how many total ways can this die land? Okay, that's the total number of outcomes is 1/6. Okay, so the answer is 1/6. And you could go through the motions of saying what's the probability of not rolling a 3, and you could take 1 minus this, and you'll get the answer just like we've been doing before. Okay, now the next problem is a little bit different from what we've had, but it's not that big of a deal. Let's say you roll a 6-sided die one more time. What is the probability that you roll an even number? So instead of rolling a 1 or a 2 or a 3, the problem just says what's the probability of rolling an even number. Now, even though it's a little bit different, maybe to think about ahead of time or when you first read it, it follows exactly the same rule. The probability of my event A, which is rolling an even number. The The probability of that is the total number of ways that can happen divided by the total number of outcomes. Now let me ask you this. On a die, the numbers are 1, 2, 3, 4, 5, and 6. Those are the only numbers on there. Which ones are the even ones? Okay? 2 is even, 4 is even, and 6 is even. Okay? So if I roll this die, the total number of ways that my success can happen is 3 ways. Okay? And the total number of outcomes is the total number of ways the die can land, which is 6 ways. Okay? 3 divided by 6 is 1/2, which is 0.5. So the probability is 1/2. And that kind of makes sense. If you know that a die has 6 numbers, and half of those numbers are actually even, if I'm looking for the probability of rolling an even number, half the time I'm going to land on an even number. It's the same process. It's number of ways the success can happen over the total number of outcomes. There was 3 ways to get my success. There were 6 total outcomes. So I had the probability of 1/2. Okay? And if I wanted to know what's the probability of getting an odd number, okay, if I wanted to know the probability of getting an odd number, that's the same thing as A complement, because even is the opposite of odd is the opposite of even. So if A is the probability of getting even, then all other outcomes of the experiment are going to be odd numbers. So A complement is going to be that. 1 minus P of A is going to give me the answer to getting an odd number, because it is the complement of A. It consists of all of the possible outcomes other than getting even is going to be the odd number, okay? So it's 1 minus 1/2, and I think you know just without even doing the fractional stuff that that's just 1/2. So what we're saying is the probability of getting an even or an odd number is both 1/2. That's the same thing as flipping a coin. It means that on any given time you roll the die, half the time you're going to get an even number, half the time you're going to get an odd number, just like flipping the coin, okay? There's really no big surprises there. Now we're going to get into those are fairly, I mean, once you understand it, they're fairly simple problems. You look at the number of ways that success can happen, the number of ways that the outcome can occur, and you divide them, you get the probability. Next problem's a little bit more challenging, but we're going to think through it and reason our way through it. Okay, a car rental company has 18 compact cars and 12 mid-size cars. Okay, if 4 cars are selected at random, what is the probability of getting 2 cars of each type? So just by reading this problem, you can see right away that it doesn't quite fit the mold of the other problems we've done before. It has too much information just to be a simple S over N and you're going to get the answer. I mean, you have 18 compact cars and 12 mid-size, and I pull 4 of them. What's the odds of getting 2 cars of each type? It's certainly not going to be a simple matter of just taking 2 numbers and dividing them and getting the answer. We have to reason our way through this, okay? But we're going to go back to our roots, and we're going to know, and we're going to write down that the probability of event A is always going to be equal to the number of ways it can successfully occur divided by the total number of ways the experiment can happen. A is defined to be the event where I get 2 cars of each type, where each type is compact and mid-size. 2 cars of each. That is the definition of my event A. So what I need to do is calculate the total number of ways I can have a success, the total number of ways I can get 2 cars of each type, divided by the total number of outcomes of this experiment, okay? So let's walk our way through it. Okay, let's walk our way through it. Let's switch colors and break it up a little bit. There are 12 plus 18 equals 30 total cars. The problem said that I had 18 compact cars and 12 mid-size cars. That's true, but I'm just telling you because you can add them together. I have 30 total cars altogether, okay? If I pick 4, because that's what the problem says, if I pick 4, then there are 30 with the 4 on, this is the combination back from the last section on combinations. There are 30 combination with 4 ways to choose cars. I'm not even talking about compact or mid-size. I'm just talking about N, the total number of ways to choose the cars, okay? I haven't talked about getting 2 of each. All I'm trying to do is find what N is equal to. I've got 30 total cars. I take 4 at a time. So I've got 30 cars strung out in front of us here. 30 cars. Some are mid-size, some are compact, okay? And I could take these 4, or I can take these 4, or I can take 2 from over here and 2 from over here, or I can take 1 from over here and 3 from over there. I've got a lot of different ways in which I can pick these cars. I need to find the total number of ways to do that, because that's always going to be what n is equal to, the total number of ways the experiment can occur. So I've got to find that first. So there are 30 combination with 4. There's that many combinations of way to do this. And if you recall, we'll switch colors again. nr, the combination of n and r, is n factorial over n minus r factorial times r factorial. Okay? So in this case, n is 30, so it's 30 factorial over 30 minus 4 factorial times 4 factorial. Okay? And so you have 30 factorial on the top over 30 minus 4 is 26 factorial times 4 factorial. And now we're going to do our little trick on the top, because these are very huge numbers on top and bottom. This is 30 times 29 times 28 times 27 all the way down. This is 26 times 25 times 24 all the way down. So really all I'm going to have is 30 times 29 times 28 times 27 over 4 factorial, which is 4 times 3 times 2 times 1. What happened to all this? Well, everything below, because this continues on, 27 times 26 times 25, all of these cancel with the 26 factorial when you bust it out. We did a lot of this in the section on combinations. Okay, so when you do these, you multiply everything on top and you multiply everything on the bottom, what you're going to get is 2,7,405 ways to pick cars total. All this is saying is that I have 30 cars taken 4 at a time. There's 27,405 combinations, ways to do that. Okay, so that is what n is going to basically be equal to. Okay, that we found what the denominator is. Now we have to find how many ways can we get 2 cars of each type. That's the number of ways our success can happen. We're going to divide those two numbers and get the answer. Okay, so for success, there are 18 combination with 2, 18 taken 2 at a time ways to pick a compact car. Okay, because I said I had 18 compact cars, and the problem actually says that I want 2 of each type. That's my success. So if I have 18 compact cars taken 2 at a time, because I only want 2 compact cars, there's going to be that many combinations to do that. So we're going to have to calculate that. And there's also 12 combination with 2, 12 taken 2 at a time ways to pick mid-size. All right, so we're making some progress here. The problem said the event A was getting 2 cars of the same type. We found the bottom. The number of ways to get the compact cars is going to be this, and the number of ways to get the mid-size cars are going to be that. So we need to calculate those 2 things. Now the crucial thing that you really need to know here, and this is the part that's not very obvious when you first do this problem, okay? 18 taken 2 at a time is the number of combinations to get a compact car. 12 taken 2 at a time is the number of ways to get a mid-size car. What I'm interested in is the total number of ways to get 2 of each type, okay? Because I know how many it takes, I'm going to calculate in a second, how many ways I can get the mid-size. And I know how many ways in general to get the compact car, but I want to know the whole enchilada, the whole number of combinations for both of those things put together, okay? So this is basically the fundamental counting principle. Event 1 is getting the compact car, 2 of the compact car. Event 2 is the number of ways to get the mid-size car. I multiply these things together to get the total number of ways that both of those things can happen together. Just like a phone number. You have 7 digits. There's 10 digits for the first number, 10 digits for the second number, and so on down the line. There's 10 ways to pick the first one. There's 10 ways to pick the second one. So when I'm calculating the number of ways to get a phone number, I use that fundamental counting principle. I know how many ways each digit can occur, and I multiply them together. Here I know how many ways I can pick the compact car, and how many ways I can pick 2 of the compact cars, and how many ways I can pick 2 of the mid-size cars. Those are the number of ways for each of my events. But in order to calculate the total number of ways that I'm actually interested in to get 2 of each, I need to actually multiply these together. 18 combo with 2 times 12 combo with 2. Only the multiplication here is going to give me the total number of successes, the total number of ways that I can get 2 of each type. Okay? So when you bust this out, 18 combination with 2 is going to be 18 factorial over 18 minus 2 factorial times 2 factorial. Okay, that's going to be 18 combination with 2, and this is all going to be multiplied by 12 combination with 2, 12 factorial over 12 minus 2 factorial times 2 factorial, and all I need to do is calculate that. Now you could dump it in your calculator, that's perfectly fine to do, but over here I'm going to have 18 factorial over 18 times 2 is 16 factorial times 2 factorial times, and over here I'm going to have 12 factorial, and I'm going to have 12 minus 2 is 10 factorial times 2 factorial. Okay, so I need to simplify all this. For this first fraction, a lot of these are going to cancel because this is 18 times 17 times 16 times 15 all the way down, and this is 16 times 15 times 14 times 13 all the way down. So on the top I'm going to have 18 times 17 over this 2 factorial is 2 times 1. Everything else canceled with the 16 factorial because here going down from 17 times 16 times 15, all the things there cancel with the 16 factorial. Okay? All of this and all that was left over was 2 factorial. Over here, I'm going to have 12 times 11 over 2 factorial, which is just 2 times 1. Okay? So what happened here is I canceled 12 times 11, and then times 10, 9, 8, 7, 6, 5, 4 is going to cancel with this 10 factorial, so that's what's going to be left right there. So when you get an answer here, and you get an answer here, and you multiply all this stuff together, what you're going to actually get at the end of the day is 10098. And what is that? That's how many ways for event A to have a success. So now I've calculated both things I need. I know the number of ways I can get my success. I know the total number of ways that this experiment can occur. So the probability of A is equal to the number of ways my success can happen divided by the total number of ways the experiment can happen. Okay, so it's going to be 10098 divided by 27405. Okay, and when you do that, you're going to get 0.368, which is between 0 and 1, and it has to be because every probability is going to be between 0 and 1. So if 0.5 is 50-50, this is less than that, okay, but it's still fairly likely to happen, but not really likely. It's about 36% chance of the time. So let's go back up to the top. What we were trying to do is calculate if we had 18 compact cars and 12 mid-size cars, all right, what we're trying to do here is figure out what is the probability if I pick 4 cars that I'm actually going to get 2 of each type. So I go back to my roots. Probability is the number of ways success can happen divided by the total number of outcomes in the experiment. Okay? So I need to work on each number. To find the total number of outcomes, I need to look at the total number of cars. So I have 30 cars, and because I'm picking 4 of them, just go back to the section on combinations, how many ways can that happen? Well, the order does not matter here when I'm picking cars. If I pick the Ford Taurus, and I pick the Chevy Cavalier, and I pick 2 other cars, and then somebody else comes and switches the order doesn't matter when I'm picking cars. It's not like a race. It's not like vice president, president like we were talking about in the last couple of sections, okay? So you're using combinations. So 30 taken 4 at a time in a combination is given by this math here, and you get 27,405 ways to do that. That's the total number of ways I can pull cars out of that pool of 30 cars. Now we get more specific. The way in which I can get my success is if I pick 2 of the 18 compact cars and 2 of the mid-size cars. All right? And so the way I do that is there's 18 combination with 2 ways to pick the compact car and 12 with 2 combinations to pick up the mid-size. The 2 is telling me I'm picking 2 of each. That's where I'm using that little fact in the problem. But to get the total number of ways to do it, I have to multiply them together, just like when I was doing my phone numbers. You know, if I have 3 numbers, and you know it's part of a phone number, and each number can be 0 and a 9 for 10 total digits, how many total combinations or how many total ways are there to order that? Well, you have to take event 1, event 2, event 3 and multiply them together, the number of ways each thing can happen. Well, there's this many ways to get the compact cars and this many ways to get the mid-size, so all together you multiply them. You do all that math there, you get a pretty big number. And then finally, the probability is the number of ways my success can happen divided by the total number of ways I can pick all these cars, giving me a probability of 0.368. The final problem in this section says, in a lot of 20 tires, 3 of them are defective. Okay? If you pick 4 tires at random, what is the probability that you will get 1 defective tire? Okay? So again, it doesn't quite fit the mold of the simpler problems in this section. There's just too much information just to pick your success and pick your total number of outcomes really simply and divide them. So you need to think a little more deeply. But in this problem, we still start at our roots and look at the definition of probability. So to read the problem again, there's 20 tires, 3 of them are defective. If you pick 4 tires at random, what are the odds, what's the probability that you get 1 defective tire? So we start with our roots, and we know that the probability of event A is equal to the number of ways success can happen divided by the total number of outcomes in that experiment. Okay? So S would be the total ways, the total number of ways to get 1 bad tire in your pick. That's what the success is defined to be. And N is the total number of ways to pick 4 tires out of 20. Okay? So what I need to do is work on those numbers individually and to calculate those numbers eventually. So to calculate the total number of ways I can pick the tires, that's just going to be the combination of 20 with 4, because there's 20 tires total and I'm picking them 4 at a time. So if I had 20 tires stacked down in a row, I could pick these 4 or these 4 or these 4 or maybe 2 from over here and 2 from over here. There's lots of different ways I can pick these tires, and the order does not matter. So I use combination. Okay? 20 combination with 4 is going to be 20 factorial over 20 minus 4 factorial times 4 factorial. So I'm going to have 20 factorial over 20 times 4 gives me 16 factorial times 4 factorial. Okay? Now let's go ahead and simplify. On the top I'm going to have 20 times 19 times 18 times 17. On the bottom I'm going to have 4 times 3 times 2 times 1. The 16 disappeared because he canceled with all the other terms after the 17 because they're all multiplied and divided by one another. When you multiply the top and the bottom and do the division, you're going to have 4, 8, 4, 5 total ways to pick 4 tires out of 20. That's a straight problem from combinations from the previous section, so we just had to use it to find the total number of outcomes, okay? Now, for S, which is the number of ways I can get my success, and by the way, my success is the probability that I will get 1 defective tire in my pick, okay? What I need to do is figure out the total number of ways that I can get 1 tire is bad in this pick of my 4 tires, okay? The way you do this, I'm going to write it down and we're going to talk about it, okay? It's going to be, out of 3 defective tires, I pick 1, that many combinations, times out of 17 remaining tires, I pick 3, okay? This is exactly like the previous problem, right? This thing, this term right here is out of the 3 defective tires that are in this lot. Notice that 3 plus 17 is 20. That's all the tires I have. Out of the 3 defective ones I have, I only pick 1. And out of the 17 defective tires, the 17 tires that remain, I pick the remaining 3. This is what locks down the fact that I only get 1 defective tire in my pick, okay? So you multiply them together because of the fundamental counting principle, before. If you have, a combination lock here, with 2 digits, and it's 0 to 9 and 0 to 9, okay? So I have 10 possible choices, and I would say, well, this one can occur 10 ways, and this one can occur 10 ways, and there's 100 different combinations for that lock, to open that lock. Here I'm doing exactly the same thing, okay? This is the number of ways I can pick the 1 defective tire, and this is the number of ways I can pick the remaining 3 tires. 1 defective, 3 remaining good tires in my pick. When I multiply those two together, I get the total number of ways the total number of ways that I'm going to get one bad tire and the rest good tires, okay? So we go ahead and calculate that. So what this is going to equal for this combination is going to be 3 factorial over 3 minus 1 factorial times 1 factorial, okay, times 17 factorial over 17 minus 3 factorial times 3 factorial, okay? Just straight combinations. And then over here I'm going to have 3 factorial over 2 factorial times 1 factorial times, and over here I'm going to have 17 factorial. I'm sorry, I'm actually going to have, let me write it like this. 17 factorial over 17 minus 3 is 14 factorial times 3 factorial. And let's go ahead and just simplify this and say right here, 3 factorial on the top is going to be 3 times 2 times 1, and on the bottom I'm going to have 2 factorial. 2 times 1 factorial is just times another 1. Okay? And then over here is multiplied by 17 times 16 times 15 over 3 times 2 times 1. Now what happened here, 17 times 16 times 15, everything below, the 14, 13, 12, and everything else canceled with this one. And the 3 factorial stays the same. So when you actually do all of this, the 2 cancels with the 2, the 1 with the 1, 3 is just going to sit there. What you're going to have is 3 times 4080 over 6. That's just what that second thing is going to equal to. And when you do all this multiplication and division, what you'll get is 2040, and this is ways to pick one bad tire. Okay? So now I know the total number of ways to pick the one bad tire out of my 4 tires that I pick, and up here this is the total number of ways to pick of all the combinations of all the tires. So the probability of my event A is equal to the number of ways my success can happen divided by the total number of ways that the experiment can happen. Total number of ways for my success is 2040, and the total number of outcomes of the experiment is 4845. Okay, and so the probability of event A, when you do all that math and divide it out, what you'll get is 8 over 19, and if you just wanted to convert that to decimal, that would be 0.421. So almost half the time in that case, because 0.5 would be half the time. If I had 20 tires and 3 were defective and I picked 4 at a time, just under half the time I'm actually going to get one bad defective tire in there. So that was an example of a problem that wasn't quite so clear cut, but when you get these kinds of problems, you need to use your basic definition, number of ways the success can happen, the number of ways the outcomes can possibly happen, and somehow you have to do some thinking and really figure out what it means. And that's why the topic on permutations and combinations in the previous sections were very important, because they directly come into calculating the number of ways events can happen, and the probability of an event occurring is always going to be defined as the ratio of the number of ways the success can happen and the number of ways the failure happens. So in this section we've covered that. We've talked about probability, the Venn diagrams, the definition of probability, and we've worked a whole slew of problems to get you the flavor for what you're doing. You're picking the number of ways the success can happen divided by the total number of ways the experiment can occur. That's a good basic introduction. In the next several sections we're going to talk about some more complicated probability theorems, and we're going to apply it to a little bit more difficult types of problems.